All right, so for today's lesson, we're just talking about the red blood cells. Red blood cells are abundant, the most common type of the blood cells, 4.5 to 6.3 million in males and 4.2 to 5.5 million in females. And hematocrit, which is the packed cell volume of the cells which are centrifuged, males will have roughly half of it, so 50% and over, and females will have definitely less than the 50% volume by volume. Now let's talk about the structure of RBC, and notice that we are looking at the graphic organizer and I'm talking about the RBCs. So if you're taking notes, you can take notes accordingly. Structure of RBCs are small and they're highly specialized discs. They're thin in the middle and thicker at the edge. The very specific reason for that shape and the conformation of the RBCs are as follows. Shape. By creating that donut shape and that disc shape, you increase the surface area to volume ratio. That way, it is able to absorb and release oxygen and carbon dioxide much faster on these edges. It also is better than a sphere because the spheres are going to stick together or they may want to create clots. The discs form stacks which are called as rouleaus, which will smoothly slide on top of each other through the blood vessels. The disc, because of its shape and not being a sphere, it can bend and flex, being able to go through small capillaries as small as 7.8 micrometers. 7.8 micrometers is the size of the RBC, and it can go through half its size of capillaries, 4 micrometers. So here is the view of RBC smear. So as we were talking about that, you could take the blood and then create a film on slide. So this is how it will look under 400 times magnification, low powered magnification. This would be in a high power. So this is the almost the electron microscope level. So this is how the cells will, you can visualize them at about 2000 times magnification of the normal. And you will notice, as I was talking about, the diameter from end to end, you can think is 7.2 to 8.4 micrometers for the RBC. But notice, because of its disc shape, it is able to stack, and then it is able to converge through very tiny capillaries. Lifespan of RBCs is 120 days. It is in many ways not a technical cell because it does not have nuclei, mitochondria, or even ribosomes. At this point, it's so specialized that it is just a transportation tool for oxygen. So there's no repair mechanism, and it only has some features of anaerobic metabolism. So it cannot do aerobic metabolism by itself, and its main job is transporting oxygen. Hemoglobin is the exact molecule that is a macromolecule that is conveyed or converted through the RBCs. In a normal male, you have 14 to 18 grams per deciliter of whole blood. In a normal female, it is 12 to 16 grams per deciliter of the whole blood. Point to notice, know these numbers and the range. What is a hemoglobin? It's a complex three-dimensional molecule which is made of 4 units of protein. Each molecule of protein is called heme, and it is connected at the center through a iron ion. And the iron ion is the one that has affinity for oxygen. associates easily with oxygen, and it becomes oxyhemoglobin. And when it dissociates with oxygen at a lower pressure, it becomes deoxyhemoglobin. This is the structure for that. So you have the hemoglobin molecule, there are alpha chain and the beta chain, and they're connected to each other through these heme molecules. And you can see it is iron Fe2 positive ion in the center of this. The fetal hemoglobin has a stronger form of hemoglobin. It has higher affinity for oxygen because the fetus has to absorb oxygen from mother's blood. So it's already at a disadvantage. Therefore, fetal hemoglobin is much more higher of oxygen affinity than normal blood. And hemoglobin's main function is carrying of oxygen from high oxygen concentration like lungs, and it carries it to the low oxygen concentration areas. And in the low oxygen concentration areas, hemoglobin will release the oxygen, and in those areas where the oxygen concentration is low, it is going to pick up carbon dioxide and convert to carboaminohemoglobin and transport it back. This is an example of normal RBC, and then you see the sickle-shaped cells. These are a special type of RBCs which have deformed hemoglobin, and they cause sickling of the cell or sickle cell anemia.